Okay, the purpose of this video will be to talk about vector components, and before I even get to what components are, how they're used, let's do another vector addition problem where we add them head to tail. So it says add the following vectors and draw and measure the resultant. Our vectors are 6 centimeters at 0 degrees from the x-axis, I guess that's just left off, and 4 centimeters at 90 degrees. So this one should be actually pretty simple. All we have to do is measure out 6 centimeters from the origin. Okay. Now we make our little secondary axis. And 4 centimeters at 90 degrees. That would be just straight up. Okay, and the resultant, as we know, goes from the origin to the head of the last vector. Easy enough, so we draw from here up to here. There we go, and we're going to measure that. Looks to be about 7.2 centimeters at an angle of, say, about 34 degrees from the positive x-axis. Okay, so we've got a resultant. Now, think about it for a second. Did we really need to do all of that? There's definitely another way to find that resultant for this particular case. And and the reason that there's another way to do this is because there's something special about these two vectors. So this is the angle that we measured, but notice this angle right down here. So that's a 34-degree angle. This is a right angle right here. The two vectors we were given are perpendicular to one another. So they are perpendicular. So what sort of triangle did they make when we connected? When we drew our two vectors and then we drew the resultant? What sort of triangle did that make? Because notice when it makes a triangle, it makes a right triangle. Okay, and what we know about a right triangle is that there's a trick for determining the length of the sides that you learned all the way back, probably in middle school. So we know the length of this side. We know the length of this side. We can find the length of this side without ever measuring this. Okay, we should be able to. By using what you guys know as the Pythagorean theorem, a squared plus b squared equals c squared, where a and b are the legs of the right triangle, c is the hypotenuse. That's what we're looking for here. So I'm going to do 6 centimeters squared plus 4 centimeters squared equals c squared. 6 squared is 36, 4 squared is 16, so 36 plus 16 is 52. Which means I have to take the square root of 52 to get c, the length of the hypotenuse. And you see that I get 7.21 centimeters, which is really close to what we measured. Okay, so there's evidence that that works. How would we find the direction, though? This one's a little trickier. We have to use a trigonometric identity. Okay, basically we need to use trig, and you learned that back in middle school too, and then learn more and more about it as you went through high school. The way to get the direction is to remember that for a right triangle, there are certain relationships between the side lengths and the angles of the triangle. The one we're going to look at, let's imagine we didn't know that 7.21 yet, or the 7.2, whatever you want to call it. We just know that this is 4 and this is 6. We have an angle right here, and that's the angle we like to use because that's the angle from the positive x-axis to the resultant. For this angle right here, we can name the sides. This is obviously the hypotenuse. It's the side across from the right angle. This is the opposite side because it's opposite of the angle we care about, and this is the adjacent side because it borders or is next to the angle we care about, and that's what adjacent means. So we know the opposite side length, we know the adjacent side length, and you should remember back from whenever you learn this, that there is a formula that says tangent of theta, theta being an angle, equals opposite over adjacent. And if you notice in this case, our opposite side is just like kind of like a y value. So I'm just going to put y because it goes up, and our adjacent side is kind of like an x value, so I'm just going to put an x. Now, what tan means, tan is not a number, okay? If you take the tangent of some angle, it gives you a number, but tan itself is an operation. It's something that you do, okay? So if we're interested in solving for theta, the direction, let's plug in our y and x. Y, being this side, the side that goes upwards, is 4 centimeters. X is 6 centimeters. And if we simplify that, it's 2/3 or 6.6666 repeating for forever. In order to solve for theta, okay, it's not just that theta equals 2/3. The tangent of theta equals 2/3. Remember, tan's an operation. What we want to do is get theta by itself, so we need something to cancel out that tangent. Some of you might be thinking divide by tangent, but it's not a number or a variable. You can't do it. It's an operation. We have to do the inverse of that operation to both sides. So we need to do what's called the inverse tangent. And you remember that inverse tangent is, there's a little part on my calculator that says tan to the negative first, and if I hit second, I get that option. That would be inverse tangent. If I take inverse tangent of both sides, what I end up with, tangent and inverse tangent will cancel out, and I'm left with theta equals inverse tangent of 4/6. So I do 4 divided by 6, and I do second tangent, and my angle is 33.7. And if you look, that's very, very close to what we got. We got 34 degrees. So all that got done without me ever needing, I didn't need to draw anything for this. All I needed was the numbers, okay? So it is possible to use trig and Pythagorean theorem to do vector addition in a certain case, okay? As we know, the sum of two vectors is equal to the resultant. And this also is true in reverse. Any vector is the resultant of two perpendicular vectors. Okay? So it's interesting that we have two perpendicular vectors and we add them together and we get this resultant. We could do that in reverse as well. We could have started with this resultant and found the two perpendicular vectors that add up to give us this. Now, this is important because if we can find an x, like we're going to end up calling this the x component. If we can find the sum of all the vectors in the x direction and the sum of all the vectors in the y direction for a certain set of vectors, or parts of the vectors in those directions, we can find the resultant without ever actually having to draw it. And beyond even just adding vectors together, the idea that you can take a resultant and break it down into two perpendicular vectors that have been added together has some other interesting meanings in physics. And that comes into play a lot when we talk about kinematics, and especially in our next unit, forces. So what I'm trying to say here is that for kinematics at least, the perpendicular components of motion are independent. This is why we like to break things into two perpendicular vectors, or two components as we would say, because different parts of motion don't have any effect on each other. Motion in the x direction does not affect motion in the y direction. This is why last year when we did the example with a tennis ball rolling off a table and a tennis ball being dropped from the same height, one had motion in the x direction, one did not, yet their motion in the y direction was exactly the same. They took up the same amount of time to hit the ground. This is the same idea as if you've ever seen a person on a skateboard, they jump up off the skateboard while it's moving. The skateboard continues to move under them, so that when they land, they don't land on the pavement, they land on the skateboard again, okay? In that case, the vertical motion of the skateboard and the person were independent of the motion in the x direction. Motion in the x direction was not affected by the person jumping off of the skateboard, just in the same way that the motion in the y direction of those tennis balls was not affected by one of them moving in the x direction and one of them not moving in the x direction. So that's why we care about components, because they can show us different parts of motion. They can allow us to break down motion into separate areas or separate directions that don't affect one another. Another way of saying this is what happens in the x direction does not change the y direction. Ultimately, different components either have or don't have effects on certain measurements. And we need to separate vectors into components to be sure of that. Okay? So again, ultimately what we're seeing here is that we can find the magnitude and direction of some resultant vector, not by doing head to tail addition, but by using math, Pythagorean theorem, and trig. And you can also go the other, I'm telling you right now, you can also go the other way. Not only can you add these perpendicular components up into a resultant vector, you can take that resultant vector and break it down into its perpendicular components. What we're going to talk about now is, well, that second part, okay? We're going to draw a vector, 5.4 centimeters at 60 degrees from the positive x-axis. So, let me move this down a little bit. 60 degrees from the positive x-axis, that would be in approximately this direction. I'm going to draw 5.4 centimeters, so that looks like about here. There's my original vector, okay? Now, this is what I was saying, you can also go in reverse, take a vector and break it into its perpendicular components. Again, we're going to call them the x component and the y component. The x component definition is the vector's extent in the x direction. In other words, how far does this original vector extend in the x direction? Well, you might say, okay, well, even if I just did this, I can see that the vector goes out this far in the x direction, and that's where it stops. Well, that's what the x component is. It is literally just how far does the vector, how big is the vector in that direction. And this definitely gets dashed lines, or dotted lines, however you want to do it. Okay? Now notice, this angle right here is 60 degrees. I'm going to measure this x component, and I'm going to get, looks like about 2.7 centimeters. Okay? Let's see here. Now I could also draw in the y component. The definition of the y component is the same thing. It's the same exact definition, the vector's extent, but this time in the y direction. Okay? So I could draw this in a couple of ways. I could draw the x component in a couple of ways. I could draw the y component here because this is the extent of the vector in that y direction. So I could draw it here. And I measure it, and I get approximately, looks like 4.65 centimeters. Now, don't get freaked out if you ever see them drawn differently. If you ever see the y component drawn this way, so that the x component and the y component are matched up tail to tail, that's fine. You might see the x component up here, that's fine as well. Just imagine you're taking this component and just moving it up here, or taking this component and moving it down here. So, interestingly, we could have actually found these two, the x component and the y component, without ever actually drawing it in. And we would do that using trig. See here that this is, again, a right triangle. Here's the angle between the x and y components. This is my hypotenuse. I know that it's 5.4 centimeters, and I know this angle is 60 degrees. That's actually enough to help us find the x and y components. We can find the x component, this adjacent side, by remembering that if we're looking for the adjacent side and we know the hypotenuse of 5.4 centimeters and we know the angle, Adjacent hypotenuse tells us to use the trig identity of cosine. Cosine of theta of the angle equals adjacent over hypotenuse. If you rearrange that in your head, we get that the adjacent side is equal to the hypotenuse times the cosine of the angle. And we're going to write it in physics terms here. The adjacent side is the x component. I'm going to refer to the hypotenuse as r times cosine of theta. So this would be, the x component is 5.4 centimeters times the cosine of 60 degrees. If I do 60 cosine times 5.4, I get an x component of 2.7 centimeters, which is exactly what I got. Y would be the opposite side, right? Opposite, and the other side I know is the hypotenuse. Opposite over hypotenuse is sine of theta. If I rearrange, then I get opposite side, which is really y, equals the hypotenuse, which again I'm going to call r, times the sine of theta. 5.4 centimeters times the sine of 60 degrees is equal to 4.68 centimeters. Very, very close to what I had. Okay, so we used trig to do this, to figure out the x and y components. And by the way, these formulas, x equals r cosine theta, y equals r sine theta, where r is the hypotenuse, theta is the angle. These formulas only work if the angle is measured from the positive x-axis. Okay? So now what we've done is we've seen that we can actually take a vector and we can break it down into its x and y components. Not only can we take those components and build up the vector, we can also break it down. Okay? So no matter what, as long as we're given enough information, we could either find the components if we want to, or we could find the resultant and direction, the magnitude and direction of the resultant, by only using math. I'm going to stop there. I'm going to do one more video for adding vectors together solely using trig, kind of summing up everything we've done so far, and then we'll be done with vectors.